Yeah, good morning, everybody. Welcome to the next week of KDD2. We are in the middle of Lecture 4 Sequential Data, and we talked about sequential data in general, and then the general or the more most generic type of sequence data or sequential data are sequence data. We talked about similarity models for sequence data 2 weeks ago, and this week we will talk about time series data. So a special case of sequences where basically the index set represents, or each index position represents a specific time slot, a specific point in time. We will talk about specific preprocessing techniques for time series, then again similarity models for time series, where we will have a look at simple measures and also some more specific measures like dynamic time warping, and we will also talk about feature extraction, which is quite common when we deal with time series. I'm just a little curious right now because there is a big cleaning car in front of my window passing here. Maybe you hear it in the background, so I think it's going away. Okay, so we start with pre-processing, but first of all we'll have a look at time series. First, a short introduction here. As I said before, a special type of sequence data, because the values that we have recorded are typically recorded over time, so the index set represents specific time points. And we typically distinguish between simple univariate time series, meaning we just record one value per time. For example, in stock prices, if you have the time series of one specific stock price, of the price of one specific stock, that is just one value that you record over time, or temperature curves and stuff like that. Or we can also record multiple values per time slot, and then we speak we talk about multivariate time series, like trajectories, which is a time series of spatial positions, typically 2-dimensional, maybe also 3-dimensional, or video data, combinations of sensor readings and stuff like that. It's not that it's really important to have this distinction, but people always or very often use these terms: univariate time series, multivariate time series. And I mean, if you know what is univariate and multivariate, then of course you know what the difference is, but good to talk about that. Anyway, so very often if you deal with time series data, then you get raw data from sensor readings, from some stuff, some machine that records something over time, and very often this is extremely noisy data. So the typical scenario is that you have to do a lot of preprocessing in order to get rid of noise and artifacts in the data coming from the machinery, from the data generators, before you can really do something to mine for, because the data is typically extremely noisy, containing artifacts and stuff like that. So preprocessing is very important, but one very important thing, attention, preprocessing is extremely application specific, and we will mention that in the remainder here in this subsection preprocessing also. It's extremely application specific, so always keep in mind, do you really want to do that particular preprocessing or not? So now the cleaning car is coming back, so I'm just trying to get to save some time, because you probably have some background noise. I hope that was the only interruption now. Okay, so we start with preprocessing now, and once again keep in mind it's extremely application specific. So first of all, offset translation can be extremely interesting, because we very often have time series that have a similar trend or are similar, but have different offsets, as you see here. So the red one is quite similar to the blue one, but they simply have different offsets. And maybe in your application, Yeah, application specific, you remember. Maybe in your application it's interesting to have them or to view them as similar and forget about the offset, the different offsets. If your application is specific about the offset, then offset translation is not a good idea, obviously. Yeah, but if you are not so interested in the different offsets, then an offset translation, also known as shifting, might be a good idea. Yeah. So what you do here typically is that you move each time series by its mean. Yeah. So you take the mean. So MQ is the mean of the time series Q here, and you move the Q by the mean. Yeah, and the same with O, with the time series O, and you end up in something which is around where the mean is obviously 0 then. Yeah, so you get something which is around 0 here, and they have now the same offset. Once again, if your application thinks, or if you think in your application it makes sense to do that, then you can get rid of these different offsets and see that those two time series that those are the same like here are very similar. Yeah. And now they, for example, if you apply something like the Euclidean distance, the Euclidean distance is much smaller here than here, obviously, or here. Yeah. Yeah, that was offset translation. You can also have very often time series that have similar trends but different amplitudes. Yeah, so in German it's Ausschläge. Yeah, so you see it here. They have similar trends. It's going down and then up, and then down again, up and down. Yeah, and the same here, a little down and then up, and then down and then up and down. And here in this up, you have a kind of dent here, which you also have here, but the amplitude of those patterns is much different here. Yeah, and you can scale that amplitude. Yeah, so if you want to, if your application or for your application makes sense to scale the amplitude, you can move each time series by its mean and normalize the amplitude by the standard deviation. So this is a so-called normalization, which is a shifting and a scaling. The shifting is done using the mean, like before, and the scaling is done using the standard deviation typically. Yeah, so here you see the formula. So you take the original time series minus the mean of the time series times divided by the standard deviation of the time series, and you do that with each time series, and you see that here that now they have at least a comparable amplitude, yeah, Ausschlag, along the x-axis. Of course, the y-axis is always the time, of course, yeah, and those are all univariate time series, of course. Yeah. Okay. Yeah, another thing that people very often do, if it makes sense from the application side, is trend elimination, at least linear trend elimination. You can also do nonlinear trend elimination, but that's a little bit more complex. That is if you have similar time series with different trends, yeah, like here. So they seem to be similar, but this has a much more ascending trend than this one here. Yeah, and if your application, from the application side, it makes sense to remove this trend, then you can do trend elimination, where you determine the regression line of each of the time series and move each time series by its regression line. Yeah, gets of course a little bit more complex when object features when an object features more than one trend. Yeah, so if you have if one time series has more than one trend, so this have one trend, one clear trend, and this one, if you have more than one trend like this one here, then it gets a little bit more complex. Yeah, but anyway, you can do that, no problem. And you see here that if you do offset translation, amplitude scaling, and trend elimination, they are quite similar, those two time series. Yeah? If you just do trend elimination, or just do offset translation and amplitude scaling, you end up here. Yeah, you still have clearer trend of the green one. And if you do also the trend elimination using the regression line, you get some really comparable time series. Once again, this is the raw data. This is the processed or pre-processed data. It extremely depends on your application if this makes sense, yeah. Or you want to work with those raw time series, or you want to work with pre-processed time series. Yeah, it's really important to consider that. Yeah, and last but not least, noise reduction. Yeah, you very often have a lot of noise where the time series goes up and down and up and down. Yeah, in a very small time scale, but in also very small value scale. So if you have similar time series but with a large portion of noise, then a noise reduction, also called smoothing, can be done by normalizing over a range of values using a sliding window. For example, replace the ith value with the mean value of the 2k adjacent values. So you take this one here and remove or replace this value here, I, by the mean of this whole window here, and the whole window has a size of 2k values. Yeah, so you look at k values to the left and k values to the right, and then take the mean value of all those 2k values and replace the middle one here with the mean value, and then you just shift this sliding window over the whole time series. Yeah, and of course you have to do a special workaround at the beginning and at the end, but that's okay. Yeah, that's easy. Yeah, and then you end up from those raw time series here to those pre-processed time series, which look much better than those guys here. Yeah, and also much more similar, by the way. Yeah, and just a short summary. So there are many more types of distortions that can be removed. Again, once again, attention, a warning, it's extremely application specific. So you might also destroy patterns by pre-processing, so be very careful about it. And here's just an example where pre-processing really makes sense. So here are the raw time series from 3 classes, the blue ones, the green ones, and the red ones. If you apply hierarchical clustering using single link on the raw data using Euclidean distance, you end up in something which is not really what you want. Yeah, it's not a clear distinction between those 3 classes. So it's a very it's mixed vegetable here, obviously. Yeah, and if you do noise reduction, trend elimination, scaling, then and do the same clustering, then you end up in a clear cluster structure where you have the red ones here in this cluster. This node represents the red ones, sorry, the green ones, and this node here represent the blue ones. And that's exactly, in that case, exactly what you want. But once again, this is just an example of one specific application. In another application, maybe noise reduction or, I don't know, trend elimination is not what you want. Yeah, so be very careful about the whole thing with pre-processing.